Okay, so we've already learned how to find a confidence interval if we have a proportion, but what happens when we have a mean instead of a proportion? When our sample sizes are small, normal models don't always work, and our test statistic, that's our z-value, it's not used. Early in the 1900s, William Gossett was a mathematician, and he was actually a statistician, and he worked for Guinness Brewery. He was in charge of conducting experiments at the brewery to identify the best barley variety. While working with beer, he was limited to small data sets because you can only drink a certain amount of beer in a sitting and get valid results. I'm sure you know what I mean, or maybe don't. At the time, they were using a normal model, and he was surprised to find that that the models weren't as accurate as he thought he would be. So this led him to develop a new model that accounted for the additional variability. The reason it wasn't very accurate is because you're estimating the population mean and you have to estimate the standard deviation as well. And so you're introducing two sources of error. So instead, he developed a model where he uses the sample standard deviation and so that's what we use for estimating a confidence, or for constructing a confidence interval for a population mean. So it's funny, Guinness wouldn't let him publish his results under his name because they didn't want other companies to steal their secrets, and so he had to publish it under a pseudonym, and he called the distribution, instead of the normal distribution, it's the student t distribution. So student t distribution looks very much like a normal distribution, except that it's a family of curves. It's not one single curve. If you look here at there are three different curves. Actually, there's a whole bunch of different curves. So this blue one here is very similar to a normal curve, and that's when I have a sample size of 30. This green one here, that is almost a normal curve, but if you look, it's a little flatter at the top and a little higher at the bottom. That's with a sample size of 5. And then if you look at the red one, this bottom one, that's with a sample size of 1. I have a really flat top and high bottoms. So it depends on your sample size what the curve is shaped like. It's similar to a normal curve, but it depends on your sample size. So properties of, and the test statistic, we call it a t-score, not a z-score. So properties of the t-distribution, like the z-distribution or a normal curve, it's a continuous distribution. So it continues, extends both directions indefinitely. Like the z-distribution, it's bell-shaped and symmetrical. There's not one t-distribution, but a family of t-distributions. All t-distributions have a mean of 0, but their standard deviations are different according to the sample size. The t-distribution is more spread out and flatter at the center, however, the standard normal distribution. However, the larger our sample gets, the closer we get to a normal distribution, and 30 is about the threshold for that, a sample size of 30. So conditions to have a valid small sample confidence interval for mean. First of all, our sample has to be random. It has to be selected from the population that we're looking at. And the data has to come from a population that's normally distributed, or our sample size has to be large. Since we often have small sample to use in order to estimate the population mean. We have to use the t-distribution to account for its variability. So using our t-distribution, you can refer to the t-distribution table. It's in the back of your textbook on page A14. There's another additional piece of information you will need to look up your t-distribution. Because it's a family of curves, you have to take into account the sample size, and that is something that we call the degrees of freedom, and that is your sample size minus 1. So if I'm looking at the t-distribution chart and my sample size is 10, I have to look up I have to use the chart for 9 degrees of freedom. And you look it up the same way that you would look up a z-score. You'd find the area you're interested in and find the corresponding t-score. So for example, and by the way, there is a calculator way to do this as well. I'm going to tell you about it because you've had enough experience with the calculator that hopefully you can figure this out and not have to use the table. So if you go to distributions, and if you've forgotten how to do that, that's second button, the blue button. And then you hit the variables button, and that's where underneath that button is distribution. And then you should scroll down until you find number 4. And that would be inverse t. That's when you know the area and you're looking for the t-score that goes with the area. So when you find that, you'll see that you have to either it's going to prompt you for area and degrees of freedom, or you have to put in the area, depending on how old your operating system is, degrees of freedom, and close your parentheses. All right, so we're going to calculate a few t-scores. We want to find the t-score if our sample size is 15 and we want to use a 95% confidence level. Okay, so I always find it helpful, and I would strongly encourage you to draw a picture of what's going on. So in the middle of my my values, t is equal to 0, and I want to find the t-score that bounds the 95th percentile on both ends. All right, so over here I have my value left in this end, or tail, would be 0.025, and the same in this end, 0.025. So I'm looking for alpha over 2, which is 0.05 divided by 2, which happens to be 0.025. And then I need the other corresponding value over here. One will be positive, one will be negative. And while I'm at it, I'm going to calculate the degrees of freedom. So that's going to be 15 minus 1, which is 14. And you can look that up in the table if you'd like. You'll be looking for 0.025, the closest area you can find to 0.025 in where the degrees of freedom are 14. I, however, am going to use a calculator. So I'm going to go and find the inverse t. Remember, it's second, variables, number 4, and up pops inverse t. And mine asks for the area. So if I could find 0.025 or I could find 0.975, either one is going to give me one of the values of my t-score. And then it's going to ask you for degrees of freedom. And we already know that's 14. And when I calculate that, I get a t-score of plus or minus 2.14. Okay, you can just keep 2 decimal places with this. Whether I find the positive one or the negative one, it doesn't matter. I need both of them. And then the next example, find the t-score if n is 8. So our sample size is 8, and we're looking for a 90% confidence level. So our alpha value is 10. And remember, alpha is our error level. So here in the middle, t equals 0. Oh, over here I didn't fill that in. That's 2.14. And this would be negative 2.14. Those are my t values. Just like z values, we call them test statistics. And we are actually going to work with a few more test statistics, not today, but at some point. So t alpha over 2. I'm looking for the values that bound the middle 90%. That leaves 10% on each end. So, and if I divide that in half, I get 0.05. I could have made this over here 0.05 and probably should have. Anyways, so to find my t-score, then I'm going to inverse t. My area is, I just need one of these t-scores, so 0.05. And then the degrees of freedom this time are not 14, but since my sample size is 8, n minus 1 would be 7. And when I calculate that, I get plus or minus 1.89. All right, why don't you shut this off? Try the third one on your own. Turn it on when you're ready to check your answer. Okay, so in the middle, t is equal to 0. We're looking for the t-scores that bound the middle 98% of data. That leaves me with 1% on each end, because 1 minus 0.98 is 0.02. Divide that in half for each end, and you have 0.01. All right, and our t.01, actually not 01, but this would be t.01 and this would be t.99. Okay, so inverse t, area is 0.01, and our degrees of freedom are 25 minus 1, so 24. And I end up with t equals plus or minus 2.80 when I round. Okay, now that you know how to find the t-score, you can use the t-score to find the confidence interval, just like we did before with the proportion, only our formula is just a tad bit different. It's the mean plus or minus our t-score times our standard error here, our standard error, and that really depends on our sample size. So that's the formula you're going to need. Let's go ahead and calculate some of this. All right, so how much time do Americans spend eating or drinking? Suppose for a random sample of 1,001 Americans, age 15 and older, the mean amount of time spent eating or drinking per day is 1.22 hours. So we need that information, that's our mean, with a standard deviation of 0.65 hours. We also need that, if you remember the formula from the last slide, and we want to construct a 95% confidence interval. So let's find the t-score that goes with our curve here. If we have 95% in the middle, that leaves 5% to divide between the two ends, so 0.025. Unfortunately, we can't use the t value we found before because we have a different sample size here. Our degrees of freedom are going to be 1,000, which means this is really, really close to a normal curve. And I would be surprised if our value wasn't the same as a z-score would be. But let's go ahead and calculate it and find out. So inverse t, and then when it prompts you for area, it's 0.025. And then when it prompts you for degrees of freedom, that's 1,000. And t of 0.025, when we have this large of a sample, is plus or minus 1.96. That would be the same as a z-score. Okay, so let's go ahead and calculate the confidence interval. Our lower bound is going to be the mean, so 1.22 minus 1.96 times our standard error. Our standard error is the standard deviation divided by the square root of the sample size. And in a calculator, you're going to need to do the fraction and then multiply by 1.96, or you're going to need to put parentheses around that, and you can put it all in one step, I think. Anyways, I got 1.18 for my lower bound. And then my upper bound's going to be the same thing. I'm abbreviating that, by the way, lower bound, upper bound. 1.22 plus 1.96 times the square, 0.65 divided by the square root of 1,001. And calculating that, I get 1.26. So that's the upper boundary of my confidence interval. So if I ask you for a confidence interval, abbreviating that too, you're going to put the lower bound. Oops, I don't want that. That was premature. I need to erase. Really, I meant it. Erase. Okay. Okay, so 1.18, and then you're going to put a comma and your upper boundary. So that's the confidence interval. That's the lowest value. That's the highest value. And then if I want a confidence statement, my statement is that, I wish I could just say it. We are, and you will feel that way too, 95% confident that the average number of hours Americans 15 or older spend eating or drinking is 1.22 hours plus or minus 0.04 hours. And that's a statement, different than a confidence interval. Okay, I want you to try the last one. Turn this back on when you're ready to check your answer. And oh, look, you have data here. You do not have the mean or the standard deviation given to you, so you're going to need to find that. Hopefully you remember how. It's going to be stat, edit, list 1. You'll put all of this stuff in list 1, and then you'll quit that stat, calculate one variable stats. All right, go ahead and turn this back on when you're ready to check your answer. Okay, so I ran all that through the calculator. Hopefully I have the right numbers in there, but I got a mean of 38.25. And it's a sample standard deviation, and it rounded to 10. It was actually 10.00, but I'm not gonna write the 2 zeros. All right, so we want a 90% confidence interval. So draw yourself a picture. 0.9% of our data has to be here. That means that my t-scores are gonna bound these two ends. That leaves 10% for each end. If I divide that in half, I get 5% in this end, 5% in this other end. So I'm looking for t of 0.95 and t of 0.05. Okay. Now, finding the t-score is going to be inverse t, or the table. And the area is 0.05. Then our degrees of freedom, well, we have 12, so our degrees of freedom are 11. And calculating a t-score for that, I get t equals 1.80 plus or minus. When I round it, it's 1.80. So go ahead and calculate the lower boundary for our confidence interval. And that's going to be my mean, 38.25, minus 1.80 times my standard deviation is 10, and then the square root of my sample size, which happens to be 12. And when I calculate that, I get 33.05. Okay, so for the upper boundary, same thing, only this time I add. And I end up with 43.45. Hopefully I've done everything correctly. Okay, so the confidence interval then is 33.05 to 43.45. All right, and then if I wrote a confidence statement, we could say we're 90% certain that babies first crawl at 38.25, weeks, plus or minus 5.2 weeks. Right, because the difference between my average and the lower boundary here is 5.2, and the same thing, the difference between my middle and my upper boundary is also 5.2. All right, that's it.